Hi guys, we're live with Sonny, one of the brightest minds from NASA behind Dream Level warp drive. Today we will discuss the possibility. Hi, Sonny. Today we will discuss possibility of faster than light deep space exploration, the ability for our generation or next generations to travel to other galaxies and maybe, just maybe, have the beautiful Star Trek reality of in our life. So, hi, Sonny.
Hey, how's it going, Aaron? It's good to see you. Thanks for having me today. Enjoying getting a chance to visit with you. And I have to say, I really like the the beautiful view outside of your window. It's probably a lot prettier than the view outside my window as my blinds are closed, right?
Yes. But you are sitting in a lab where everything's happening. So okay. I guess you're somewhere in NASA right now. Is it right?
I'm just outside the north gate of Johnson Space Center. I worked at NASA for just at 20 years and left NASA in 2019, December of 2019, to join Limitless Space Institute as the Director of Advanced Research and Development. And so we have a lab just outside the north gate of Johnson Space Center. So that's where I'm at. And yes, there is a lab just on the other side of these monitors right here.
I could easily switch. I could easily give you the beautiful view and use that for the place you have. So, so the question is pretty simple. What's the story of the warp drive? Because it feels like that you are one of the greatest engineers I have ever seen, and it's not like a dream for you. It's an idea, and it's a project, and it feels like you know how to create it. But could you help our audience to understand what drives you to that project? What's the story about? What's the story behind all of that?
Yeah, how did I even get into this kind of thing? Why am I so passionate about it? Yeah, just a little bit of background. I was military brat, so I moved all around the United States. But I spent a lot of time as a teenager living just outside of Washington, D.C., and got a chance to spend a lot of time in the National Air and Space Smithsonian. And, I've always been an engineer, scientist kind of minded person, trying to understand how things work. But getting a chance to walk those halls of the Air and Space Smithsonian and seeing those illustrations of humanity working together to try and achieve some amazing things, right? That really connected with me on a fundamental level, and it just resonated with me. And it's not just about the things, right? I mean, there's some, if you've had a chance to go to the National Air and Space Smithsonian, they have some amazing illustrations of aerospace technology, but it's not just about the things. It's also about the people that worked together to accomplish those things, some compelling stories. And so I think I've always been interested in space as a result of that. And so, when you talk about space exploration, right, a lot of TV shows and movies also tend to influence the visions and the hopes that we have for the future. So I think I always leaned towards space exploration, and then what's the ultimate end goal? Well, the ultimate end goal is to get human beings to other star systems, right? In terms of exploring the frontiers as far as we can go. And so I think I recognized early in my career that engineering by itself was not sufficient, and my interests were starting to revolve around things that would be categorized as physics, if you will. And so, I got a master's in mechanical engineering, but I switched to physics, got a PhD in physics, because I always wanted to really explore the idea of a space warp and its mathematical formalism, right? And so that's the journey that took me down a path that allowed me to develop the skills and capabilities to do that. And so, just to talk for 90 seconds or less about the idea of a space warp, right? General relativity as a mathematical formalism establishes something I call the 11th commandment of physics. Thou shalt not exceed the speed of light, right? And so that's a hard speed limit. But that same mathematical framework provides a couple loopholes that allow us to potentially deal with that and still get to another star system in a fraction of a human lifetime, right? And so those two loopholes are the idea of a space warp and the idea of a wormhole. And so I'll just kind of stick with the idea of a space warp. And so the idea of a space warp works on the principle that space can expand and contract at any speed. There's no speed limit. And we know when we look at the history of the cosmos, right, that in the very early universe, there was an inflationary phase where right after the Big Bang, there was an inflationary phase. And if you think of this as like a loaf of bread with raisins in it, the raisins would have followed a path such that it looked like they went away from one another at a very, very high rate of speed, like 10 to the 30th c, right? But nothing locally ever exceeds the speed of light. Space expands and contracts in a way that makes this trick possible. And so this is one of the loopholes that we could potentially use to allow us to go to another star system. And so Miguel Alcubierre wrote a wonderful paper in 1994, published it in Classical and Quantum Gravitation journal that kind of captured the mathematical formalism for that. And there's been a number of other papers since then. But anyway, that's kind of maybe a little bit longer answer than what you intended. But there you go. That's how I kind of got interested in it.
That topic is so breathtaking for me that I could not just jump in and ask any questions trying to stop you. So I will just try, let's say, create the bite-sized pieces of information for our audience, and let's try to understand the basics. The basics is that the physics is a theory currently, and we're trying to find the understanding better than we have today. So the laws of physics is not a laws itself. It's just ideas. The best idea to explain what we have seen, and we're still willing to go further. And what you are doing right now, it's one of the most beautiful applications of that exploration. I mean, exploration of that science. And if you will be successful, we could create space civilization. And I will ask a simple question regarding all of that. Do you feel it's possible during our lifetime?
Do I think it's possible within our lifetime?
Yes,
right?
yes.
So that's probably the most popular question I get in every discussion I have with folks. That is like question number one that comes up, and it's question number one here, right? When is this going to happen, right? And I totally respect the motivation for that question, and I understand where it comes from. And so, my position on it is as follows. I don't have a crystal ball any more than anyone else does, and so that kind of, I think that frames the answer I'm about to give. And so, therefore, I don't know if it's going to be 2 years, 20 years, 2,000 years, or whatever, right? But I do know what I need to be doing next, right? And so. And let me back up and kind of give a different illustration, if you will, to communicate the concept. A couple of years ago, I was at Strasbourg, France, teaching at the International Space University. And while I was there, I got a chance to see the Strasbourg Cathedral. It's just breathtaking, absolutely beautiful construction. And if you look at the history of this beautiful building, it was they started building it in 1100 AD, right? So a long time ago. But they didn't finish it until like 1750. So it was a very long construction process, right? And so all that to say, the people that built the foundation or the basement, if you will, had no hope of seeing the final construction. They could only envision it in their head, but they knew they had to do their part for the next generation to be able to do their part. And so in my mind, in a day and age where we understand the principle of working together is valuable, we've kind of forgotten that it's also valuable to work together over generations, right? When we live in a day and age that if we text somebody on our phone and they don't text us back in 5 minutes, we're like, hello, where are you, right? And so we've kind of gotten into this lifestyle where this kind of influences how we view things. So I think it's important. We need to remember it's also valuable to work together over generational things as well. And so I'd love to see something happen in my lifetime, but I have no idea if that is even remotely possible. But I know the things that I need to be working on right now. There are specific things that I'm trying to work on to further our understanding of physics beyond the kind of the two standard models, if you will, in general relativity and quantum mechanics that kind of bookend what we know. And so I'll continue to chip away at that and try and push back the darkness for as long as I can. So
Got it. And what's the next step? What's the next real step you need to? What kind of piece of technology do you need to have to make the next step? I mean, in terms of creating the web, right?
Right. I think there's a couple things to talk about here, and one has to do with some of the open issues with the idea of a space warp. But let me back up a little bit and say, you talk about what's next. And so I hinted in my previous answer, there are two standard models of physics. If you think of physics as a Venn diagram, right? There are two circles that exist on this Venn diagram, and they kind of touch at a single tangent point between the two circles. In one circle is the word quantum mechanics, and that helps us understand how the microscopic world behaves, how atoms behave, molecules, and so forth, right? And so it's an amazing understanding of nature at the microscopic level, and we have solid state technology as a result of that. Transistors are only possible because of our understanding of quantum mechanics. And so computers, cell phones, digital age, right, is empowered by that level of understanding. If you switch to the other circle, you have the words general relativity, right? And that helps us understand how stars move and the cosmos evolves. And we can kind of understand the things that we see when we look out at the stars and the galaxies that are around us. But from a practical perspective, the global positioning satellite system, right, the atomic clocks that are on board the GPS, software has to account for general relativistic time dilation and special relativistic time dilation. So the height in the gravitational well causes a time dilation, and the speed also causes a time dilation. And so those have to be accounted for because the atomic clocks are precise enough so that those are impacted, that the resolution that is impacted. And so whenever you use your cell phone to go navigate, to go see a friend, right, that's only as accurate as it is because the GPS system accounts for that. So just that knowledge of physics, just those two circles, right? We use those every single day. Think about a day. It's funny to think in 1980 we couldn't imagine this, but now we couldn't imagine life without it, right? But that level of understanding of physics helps us immensely. But those two models are not compatible. General relativity and quantum mechanics are not compatible. So the physics community recognizes that we have a more generalized framework that we have yet to understand. And some people might use the term grand unified field theory or whatever. I think
the theory of everything, they call
it. The theory of everything, right. But in my mind, I don't think it's going to be such a Boolean switch where we just go from general relativity and quantum mechanics to all of a sudden we have this theory of everything. I think just like anything, we'll continue to have evolutions of models that maybe expand those two circles so they start to overlap a little bit, and over time we'll continue to evolve our understanding. But that's, in my mind, that's something we need to definitely explore to try and understand what are some things that we can do next. Where is the next E equals MC squared equation, right? Think about that. E equals MC squared. Oh, you were going to say something? Sorry.
No. I'm just willing to understand. For example, if we, as a human beings, could not travel through time and space right now, maybe we could send some sort of device or some sort of quantum level video cameras or something like that, and just capture the images thousands lights away, thousand light years away from us. What do you think about that? Is it possible? Is it complicated? Is it easier, cheaper? Is it achievable? Because it feels like it's the first step from my perspective. Maybe you're still thinking that we need a couple thousands of years just to get to that level.
Well, so at the end of the day, whether you're sending so if we're talking about the idea of a space warp, right? And whether you're talking about small or big, like with a lot of things, small reduces some of the energy requirements, but only so much, right? Because at the end of the day, you still have to fully understand the physics of what's going on. So in the context of general relativity and quantum mechanics, the idea of a space warp, you take the mathematics and put it into physical form. It kind of looks like talking about Alcubierre's model, for example. Alcubierre's model if you look at the field equations, it traces it to what a spaceship might look like. There's some central structure. Imagine a football-shaped type of device, and then around that football-shaped device, there is a toroidal ring. And so that apparatus would travel right along the axis of that outside ring. And so the outside ring has to have something called exotic matter. When you look at the field equations of a space warp, it requires something called exotic matter. And so in the context of general relativity, that means like negative mass, and it violates all kinds of energy conditions. And we really don't understand how to manifest the idea of negative mass in the context of general relativity. It causes a lot of concern when something requires that. And so that's a potential obstacle that we may never overcome. But again, in the context of what we know of physics, you got general relativity in one circle and quantum mechanics in the other circle. And in quantum mechanics, there's actually something called negative vacuum energy density that may serve as a proxy for the idea of exotic matter, because it has all the same mathematical characteristics of exotic matter. And point in fact, Alcubierre highlighted that in his 1994 paper, right, as an alternative to exotic matter. And so I'd like to explain what negative vacuum energy density is for listeners that may not know, but I want to take a pause and let you ask any separate questions that you want to ask me real quick. So.
It's truly interesting. Let's go through Alcubierre theory, and I guess he's living somewhere near my place in Mexico. So I don't know. Maybe I guess he's working in a capital of that country. And let's go through his theory. But later, let's discuss other possibilities. Maybe also that will also could get the same results, or at least give us other perspectives to get that traveling through time and space cameras.
Right.
Let's go with all the possibilities and problems of Alcubierre model. What do you think about that? Because I know you were working with him for, let's say, decade or slightly less.
So I've been working on the idea of a space warp for quite some time. Miguel Alcubierre and I, we don't travel in the same circles, so we haven't worked on projects together per se. And of course, that's not anything unique in the domain of physics. It just depends upon your zip code. So, you know, I work at NASA supporting human spaceflight for many years, and then I did advanced power propulsion at NASA. And so I believe Miguel Alcubierre has done a lot of work in numerical relativity, and so we're on kind of different beats, if you will. And so just haven't had occasion or reason to collaborate on this particular topic. You know, going back to the idea of a space warp, you were talking about small versus big. And in my mind, at the end of the day, we still have to kind of figure out these fundamental things, like how do we manifest exotic matter or some proxy for it to make the idea of a space warp work, number one. Number two, there are a number of other issues that could potentially cause problems with the idea of a space warp. And so in my mind, I really think we have to have a more generalized understanding of either quantum mechanics and or general relativity, some deeper framework. And in my mind, I think that's what's really necessary to maybe envision a day where we could send, whether it's robotic denizens, as you suggest, to be followed by us at some point in time if we ever got to that level of capability. But I agree with you. I think certainly if we ever did figure out how to do the idea of a space warp, we would send robotic denizens first and foremost, because you can make them considerably smaller, right? With just some awesome electronics to go through and find some incredible science long before we decide if we want to go ourselves and take a further, deeper look at something. So, but this is at some indeterminate point in the future. So who knows, right?
Okay. So from your perspective, do you know any projects working with Alcubierre model successfully, let's say, at least showcase his ideas not on theoretical side, but on practical side? Do you know any, open projects? I don't know. I don't want to be part of any secrets, but I'm just willing to understand. Do you know any projects which successfully represents and that theory with some beautiful, let's say, real life, let's say, experiments or results?
Yeah. So let's let's talk about the negative vacuum energy density stuff for just a moment as a prologue for how I'm going to answer that question. So in quantum mechanics, there's this thing called negative vacuum energy density, and it arises as a result of something called the Casimir force or the Casimir phenomenon. And so what is the Casimir force or Casimir phenomenon? Well, in the context of quantum mechanics, owing to the Heisenberg uncertainty principle, empty space is not really empty. There are virtual particles that pop into and out of existence all the time, these vacuum fluctuations, if you will, this frothing sea of virtual particles. And so and this is a little counter to what we think about the world in our big classical physics perspective, but it does have some real observational consequences that we can observe manifested in the form of the Casimir force. And so think about the following thought experiment. Imagine that my hands are two metallic plates, right? We can put those in very close proximity to one another. And when it's not this big, it's just like micron or nanometer size. These are very tiny plates, 40 micron plates, 40 by 40 micron plates, separated by less than a micrometer. So very, very tiny, tiny things. And we're going to conduct a thought experiment where we put these two plates into a vacuum chamber. We turn on the vacuum pumps so that the vacuum pumps pull out all of the air. So there is a perfect classical vacuum. There's no air molecules in there whatsoever. And so we're going to pretend for a moment, Aaron, that you have superpowers that you haven't let us in on, and that you can shrink yourself down to being a tiny atomic person. We're going to ask you to go inside the vacuum chamber and then go make some measurements for us of the pressure on the outside of the plates and the pressure between the two plates. And so our classical physics experience, right, the macroscopic world we live in, we anticipate that you're going to report back to us zero pressure on the outside of the plates and zero pressure in between the two plates. That's our expectation. But what you're going to report back to us is zero pressure on the outside of the plates and a negative vacuum energy density in between the two plates, which is coupled to a negative pressure, as weird as that might sound. And so what's happening is those two plates are restricting which vacuum fluctuation wavelengths can appear between those two plates. So when you integrate over the full spectrum of the vacuum fluctuations, there's a deficiency of what can appear in between those two plates. And so there is a lower vacuum energy state in between those two plates. And so that negative pressure wants to pull those two plates together, right? And so that phenomena was derived in 1948 by Casimir. He was working with fluorescent lights of all things. And it was measured to the community's satisfaction in 1996 by Lamoureux out on the West Coast in California. And it's been explored extensively by other folks since then. Point in fact, the Casimir force also has something called the transverse Casimir force. So as you try and slide those two plates relative to one another, the vacuum has a stickiness, if you will, that impedes the sliding motion of those two plates. So this peculiarity of nature at the microscopic level is a very real phenomenon, right? And we've measured it. And so this negative vacuum energy density, as I said earlier in our discussion, right, that has the right look and feel of exotic matter in the context of general relativity, right? So that's the background. In my mind, that's a very important thing we need to be thinking about. And so before I kind of get into something we're working on that traces to that, I want to pause and hand you back the microphone.
Okay, basically the whole question of mine is how that could help you to create the warp drive. What does it mean for warp drive? Is it the source of energy? Is it the source of some sort of creating some sort of space, special space, conditions, how that will help you creating the Alcubierre sphere? Right. Yeah, Aaron. So when I kind of gave you that little word picture of a warp spaceship, what it might look like, where you've got this central structure where the sensitive instruments might be, or the crew might be, surrounded by this donut that goes around it, and the donut has to be able to manifest exotic matter or negative vacuum energy density. And so when you talk about how could you manifest that negative vacuum energy density, the Casimir phenomenon is a way to do it. And so some of the work that we're doing both theoretically and empirically here in the lab is we are
we are fabricating some nanostructures, custom Casimir cavities, where we're trying to explore some characteristics of the quantum vacuum as it manifests inside that Casimir cavity. And so the two plates that are separated by some distance is typically kind of just assumed that it's an isotropic distribution of negative vacuum energy density. But we feel that there's a little bit of structure to it. And so that structure can potentially be coupled to a polarization field in the quantum vacuum. And so we've taken to try and manufacture custom Casimir cavities that have pillars in between the two plates. You have the two plates, and then we have like these pillar structures, flagpoles, if you will, that exist between the two plates. And it's channelized so that we can try and detect this polarization field. And so in the process of studying how the quantum vacuum responds to these structures that are in between the two plates, we want to make sure that the real structure that we're putting there doesn't, how big of a diameter can we make those pillars such that they don't start to screen themselves from the very phenomena we're trying to detect. And so in the process of doing the study of how the quantum vacuum responds to the pillars inside those Casimir cavities, we discovered that the energy density distribution, it kind of looks like a lenticular type of concentration of negative vacuum energy density around the pillar. And so qualitatively, that distribution looks like a two-dimensional section cut of that starship concept I just told you about, that little donut that goes around the little football. If you cut that starship in half and looked inside the two-dimensional section cut, you'd see a lenticular distribution of negative vacuum energy density. And so we were like, that's pretty interesting, but it's not toroidal. So how can we modify our little models to realize a toroidal ring of negative vacuum energy density more akin to what's required from the Alcubierre metric? And so we modeled a 1 micron diameter sphere surrounded by a 4 micron diameter cylinder. So just to kind of do a little hand puppet here, let's see. All right, you just got like this, a small little ball that's inside of a cylinder, if you will. And so, sorry about my primitive puppets, but this communicates, I think, right?
Yes.
And so the negative vacuum energy density that manifests as a result of this real structure is such that it is predicted to manifest a real nanoscale warp bubble, right? Not an analog, not some kind of proxy or something like that, but the real thing. It should be a nanoscale warp bubble. And so we published a paper in EPJC last year, chronicling that numerical analysis and finding, and highlighted to the community that we can now say to our fellow scientists that we can now propose a real structure that folks could manufacture, right? That is predicted to manifest a negative vacuum energy density that meets the requirements of the Alcubierre metric and will manifest a nanoscale warp bubble. However, it's not going anywhere. It's not doing anything. It's a static warp bubble. It's just gonna be there on that chip, if you will.
Let me help. I will just try to, let's say, restate that for the viewers of who is currently with us. You could create a wormhole. You already could create the wormhole, and basically you could control that wormhole. Is it real?
We can control the magnitude of the negative vacuum energy density based on how we size it, right? So we can't turn it on or turn it off. You just, once you make that structure and you metalize it or make it conducting, it will manifest a negative vacuum energy density and create a nanoscale warp bubble that will have optical properties. So it's like in effect a lens, if you will, a metamaterial lens. And so that would.
I have a couple of, inventions, and it was inspired by Ili Chuan. It's like traditional martial art and from Malaysia. And they're using in very advanced forms of Ili Chuan, they're using it's real fight. It's like, it's not something strange body movements. It's real fighting, like sort of boxing. But they have defense sphere. They're creating the defense sphere of them, and they control the whole sphere. And sometimes you're trying to penetrate the sphere of your opponent with different type of movements, blocks.
Yeah.
But one of the best example how you could, let's say, destroy the sphere or control the sphere of your opponent, it's push the sphere, his sphere with your sphere. So he's trying to protect his sphere, but you're just creating that like something like I don't know, like pull, or you just push his sphere with your sphere. Maybe you could control, maybe you could, let's say, somehow control that wormhole with others wormholes around. Is it possible?
So one of the things we proposed in the paper for an experimentation, this is just initial what if, right? There's still a lot of work that would have to be done. But the thought process is, what if we had a sequence of these sphere cylinder apparatuses lined up one right after one right after one another, and we had a hole bore-sighted through the entire apparatus. Could we go through and conduct an experiment where we send a single photon or a single electron through, one arrangement of these sphere cylinders, and then another one down an unimpeded race course? And can we show that the one that goes through the sphere cylinders transits that distance a little bit quicker than the other one would in the unimpeded course, right? So that would be a measure of are we seeing a change of optical index of refraction, if you will? And so the light, if it's a photon, perceives that path length as different than the other photon, right? So that might be a neat experiment to go try and conduct, but we haven't done any sizing calculations, and I don't believe anybody else has done any sizing calculations yet to figure out if that's something that we could get a magnitude of the signal that we could detect. I'd speculate it'd probably have to be smaller than 1 micron sphere by a 4 micron cylinder. Probably have to get down to the nanometer level, probably to get a point where we could start to have a hope of seeing some kind of a phenomenon, if you will. So, but it's just, we've got to figure that out, right? So.
Do you need a lot of energy for that? Do you need a lot of energy to create those small, like millimeters size spheres? How does it take, like megawatts, gigawatts?
Oh yeah, no, so that these structures would be. I don't know that we could make these things using traditional etching techniques, right? Like if you're looking at silicon wafer manufacturing techniques, the etching and layering and deposition, whatever. I don't think that those techniques would allow us to realize these kinds of structures in the way I'm envisioning them. But we do have something called nanoscribe GT printers, and I think there are a couple others that can 3D print down to the nanometer level. And so they use 2-photon polymerization. And so they can 3D print structures that might look like that. We probably need to go a little smaller than what they currently can do, but that might be something we could explore. But we'd have to metalize them, right? Because they 3D print in some polymers like photoresist. They 3D print in that, and so we'd have to come back and metalize those structures using some other techniques, right? And so once you metalize it, it's going to manifest the negative vacuum energy density. It won't turn off, right? But once you made those structures, that those characteristics are there. Then the question is how can we try and detect it, right? So is it like the little race course I just talked about, or can you maybe try and cause a shift in energy of a molecule? I don't know. That's all still forward work.
So the step number one is to try, let's say, to send a photon, to send just one piece of light, that photon, through that beautiful nano construction, and get some strange time and space results while looking at that photon traveling through that sphere. So it's the first step. And if that could some sort of way to destruct the journey, let's give us any ideas of time and space bending. I don't know how to put it right. If we will get that result, it will be the first step to understand how to jump from that place let's say, to another planet, maybe.
Well, so it's in the process of trying to explore new physics. Existence proof is always a very important thing, right? And oftentimes it's extremely humble compared to what the long-term potentials might be, right? And I talked about E equals MC squared earlier, right? The first nuclear reactor that we tested as a result of exploring the implications of this equation, E equals MC squared, was a nuclear reactor underneath the squash court at the University of Chicago, and it generated a half of a watt, right? And so, to put that in context for folks, the microwave that's in your kitchen right now can actually will process 1,000 watts, 1 kilowatt, in order to cook your lunch or your dinner wherever you're at. And so, a half a watt doesn't sound like it's very useful in terms of the first nuclear reactor. So, why get excited? But it was existence proof, right? It was extremely important to illustrate the physical manifestation of the mathematics that was being considered at the time, right? And so even if something were just as humble as we changed the transit time it took for a photon or electron to transit some course by just a couple of nanoseconds or something like that, it still would be extremely significant finding, if you will. Right. In my mind, it definitely fits in that category of existence proof. But it is still a long way to go from this nano thing to something where, either we're sending a small robotic denizen or maybe a much larger construction with you, Aaron, on board as the captain of the vessel, right? There's still a lot more work to do there. But, think about E equals MC squared to the Trinity test. That was 40 years without artificial intelligence, without computers, and in fact, without machine learning. Think about the possibility of exponential growth once we kind of understand what some of these new equations are, how we might be able to take these insights and map them to new functional technologies that we can use, right? It might be a lot quicker than we think. Maybe. I don't know.
By the way, do you trust in creative AI? Do you have any trust in creative AI? I mean, not machine learning, but creative AI, not just generation, but also synthesis. Do you have any ideas how, let's say, creative AI could help us to speed up, let's say, all of that series and speed up our development?
AI, machine learning, right? That it's definitely being explored in a lot of ways for a lot of problems that physics has struggled with for a long time, right? I think they've tried to bring that to bear for fusion, right? That's in my mind, that's another interesting area that I think about in terms of human space exploration of the outer solar system and the stars. Fusion propulsion is something that's also extremely interesting. But there are people that are trying to find ways to take everything we've been learning about the mechanics and process of AI and machine learning to bring to bear to that particular problem, right? How do you come up with, let's just stick with magnetic confined fusion for a moment. How do you go through and construct a system that can be stable and realize a physics coefficient of performance of 5 or 10 or something like that? And so AI and machine learning is providing a way to go through and explore a lot of different ways on how not to do it in the interest of trying to figure out how to get to it, right? So
yes,
maybe. I know there are people that are thinking about exactly what you're saying.
Because machine learning is just a level, and then the creative AI is the next step. Because machine learning is just analysis, and creative AI it's analysis plus synthesis. So it could synthesize new inventions, new solutions. So that could be maybe, I don't know, part of our future. And also the question is about, I have a lot of friends who is working, creating some sort of private launch pads for space exploration, creating some sort of European space programs, whatever. And what kind of things actually inspiring you right now in that field? What do you like about our current technologies, and what kind of technologies for space exploration actually interesting for you? Why do you like it? Could you, let's say, give us your perspective?
I've been really impressed with what entities like SpaceX have been able to achieve, just in the context of very well known physics and pretty well known engineering. And I think with the advent of computers and 3D printing and manufacturing and so forth, we're entering a golden age where we're able to achieve a lot of things that were just previously not possible 25, 30 years ago. And so it's neat to see our significant mastery of the art of getting to space, right? Getting from the surface of the Earth to lower orbit. And so I think it's been neat to see the development of systems and capabilities and approaches that we probably would have never thought of, right? But with our capabilities with computers and materials, we can do that now. And so SpaceX has been pioneering a lot. I know there's some other companies between Rocket Labs, Blue Origin, Relativity Space, Firefly, a bunch of different startups that are trying to fill some small gaps here and there, continuing to master the to space. But I've always been very, very passionate about through space, right? And so the optimization of power and propulsion when you try and address to space is very different than the optimization of power and propulsion when you try and talk about through space, right? So just a little illustration, if we want to send human beings to Saturn and we want to get them there in 200 days, the amount of energy that's necessary to make something like that possible is an order of magnitude more energy than it takes to get a payload from the surface of the Earth to low Earth orbit, right? So chemical propulsion can't close that. It just can't. The rocket equation is not linear and it's just not practical. And so, what do we do, right? And so in the context of known physics, known engineering, nuclear electric propulsion, right, is a way for us to be able to send human beings to every destination in the solar system, right? And so, and that's one of the things I advocated for working with the agency for a large portion of my career. So nuclear electric propulsion is a capability that as a mission planner, I would love to see get developed. And so NASA has the fission surface power solicitation that's out. So they will be potentially fostering the development of a nuclear reactor for surface power. But we need it to be in the megawatt level, right, to potentially be useful for moving humans around in the solar system. And so the Department of Defense has a program called Project Pele, where they're looking for the nuclear industry to build portable nuclear reactors that fit in a 40-foot Connex container to be able to be moved to disaster areas or secure locations, or maybe the Arctic to provide power. But that's megawatt level. And so in my mind, that's some beautiful work that's being done on making things small and compact that may be a kissing cousin, if you will, to something that could fly into space at some point in time. So nuclear electric propulsion, keenly interested in fusion. If you want to talk about sending humans to another star system, nuclear electric propulsion would still require a couple thousand years to get to Proxima Centauri. So NEP, nuclear electric propulsion, can't really do practical interstellar in my estimation. It seemed a little too long. But fusion, that's known physics. We just don't have the engineering figured out. Fusion propulsion, direct fusion drive, can realize up to about 5%, maybe 10% speed of light. And so that opens up some stellar destinations, and that's based on known physics. Just got to get the engineering figured out. But I suspect we'll see fusion in a terrestrial environment first as a power system. And so fusion has often been described as the power source of the future, jokingly, that it would always be in the future. Right. But in the last 10 years, there's been a surprise development, a disruptive development in some of the supporting technology in the form of superconducting materials. There's something called REBCO, high temperature superconducting tape. And we have the ability to manufacture this at scale, kilometer length tapes and so forth. And it can manifest extremely large magnetic fields, well beyond anything we thought was possible in the 90s, when we kind of made the assumptions that led into ITER, the 10-story tall fusion reactor that's being built in France. And ITER is very likely going to succeed in everything they want to achieve. But REBCO, high temperature superconducting tape, as a subsystem capability, has changed some of the assumptions. And so instead of only being able to achieve 2 Tesla in the center of the plasma, we can achieve 10 Tesla, 15 Tesla, 20 Tesla in the center of the plasma. And so that's allowed some organizations to propose toroidal magnetic confinement fusion reactors that are 1/100th the volume of ITER that may achieve everything that ITER is trying to achieve. Like, for example, Commonwealth Fusion. It's a big organization in the Northeast. It's an MIT spinoff. And so they may be able to demonstrate break-even fusion, if you will, a coefficient of performance between 5 and 10 by 2025. And so that's something that I'm keenly following because that has an impact on some of the things I'd like to bring to bear for space exploration. So anyway, let me pause. That's some of the things that I think about outside of the leading edge of physics stuff. These are the other things that I also trace and Limitless Space Institute traces as an organization. So
we will try, let's say, to create the recap, the text recap of that stream, of that interview, and we will send you for editing to add the links to all of the projects, and we will add all the links down below in that video during the next couple of days. So because most of that, let's say, projects is very interesting, but for some of our advanced viewers, we need to give them, let's say, time to jump in and dive and spend, let's say, a couple hours with every project you just mentioned, because every project you just mentioned is truly really interesting, and it's way more than anyone could, let's say, imagine, because we know about the Firefly. I have friends from Firefly. I know a lot of different startups, but most of them on the surface level. So it's like, which is noticeable for the public, for the general public, but some of the very important elements already in development publicly, not noticeable for us as a general public, and that's. Thank you very much for offering us an opportunity to look through your eyes to all of that elements of space exploration, and that will help us significantly, let's say, to actually understand what's possible right now, what will be possible in the next decade. Because, it feels like you are a person of actions, and you're actually willing to be part of real life space exploration. And I'm personally, and a lot of our viewers have the same feelings, and we are actually willing to become part of all of that. And thank you for giving us the touch, giving us the hints, giving us directions where to look. It was absolutely wonderful interview, absolutely wonderful stream. It's just truly inspiring.
Thank you, Aaron. I appreciate it. Thank you for taking your time, and thank you for doing what you do to try and communicate with folks and let them try and connect with some stuff. And hopefully some folks who are inspired, maybe educated a little bit, and want to go dig in and try and master a little bit of this stuff themselves, right? Because this is a multidisciplinary challenge, kind of an all hands on deck, and so no single person is going to be able to do it. We'll all have to do it together. So go study some of this stuff and think about it. Hopefully it help continue to push back the darkness, if you will.
Thank you so much. Thank you. Okay. So the stream is over.